Hello everyone. In this talk, we present unsupervised homography estimation with Coplanarity-Aware GAN. Homography is a transformation that maps the points in one image to the corresponding points in the other image, and homography estimation is a fundamental computer vision problem that plays an essential role in a wide range of applications. Common application scenarios include image stitching and video stabilization, and so on. The exited method can be divided into two categories: traditional homography estimation and deep homography estimation. A traditional homography estimation typically involves the following steps. However, traditional homography estimation usually suffers from low texture, depth parallax, and moving objects. Some deep homography estimation methods were recently proposed to improve the alignment performance, which can be categorized into supervised and unsupervised ones. Although deep learning-based methods can fully exploit the limited features to overcome the low texture scenario, they struggle in the scenes with moving objects and depth parallax. Recently, Zhang et al. Proposed a content-aware homography estimation method for learning the mask that indicates the positions of inlayers automatically. Their predicted masks are implicitly optimized as a side product of homography estimation and lack explicit guidance, which means they cannot address the plane-induced parallax elegantly. Thus, we design a Coplanarity-Aware GAN to impose the coplanarity constraint on the masks, guiding the network to focus on the dominant plane instead of all planes. Now, we introduce our proposed method overall pipeline. Giving the input images, we first feed them into the feature projector to gain the corresponding feature representations. Then, a multi-scale CNN encoder is employed to prepare feature pyramids for coarse-to-fine homography estimation. Finally, the feature pyramids are employed from top to bottom level by the homography estimation transformer to estimate the homography progressively. As one of our key proposed methods, the Coplanarity-Aware GAN is proposed to impose the coplanarity constraint for homography estimation networks. When the homography estimation transformer predicts homography matrices, we can apply them to obtain the warped feature FA and FB. Note that the feature pairs, FA and warped FA, FB and warped FB, are induced by the unique homography HAB and HBA, respectively. We thus treat them as real pairs to guide the generator to learn the internal geometric relationship between real pairs. For the fake pair, we construct it by multiplying the feature FA and FB with the mask MA and MB. The masks tend to focus on the dominant plane with the adversarial training, where the highlight areas are registerable. As shown in the bottom figure, one homography can not align planes A and B simultaneously. Our masks with the coplanarity constraint can focus on the dominant plane A. Now, we introduce our homography estimation transformers pipeline. The top-level feature pair is first consumed by the self-attention encoder, and then a weight token is concatenated with self-attention features to the class attention decoder to summarize the transformations. Next, an MLP head projects the features to a weight vector. In the next module, we first warp the feature PA2 using the previously predicted homography. Then take the warp feature and PB2 as the input of the self-attention encoder. Finally, we can get the final predicted homography by repeating the operation mentioned above. We evaluate our method using the same dataset as in Zhang et al.'s, where the image pairs are roughly evenly categorized into 5 types as follows. Note that our method achieves the state-of-the-art performance on all categories of the dataset and outperforms the best existing method bases Homo by 22%. We then investigate the robustness of all methods by computing the proportion of inlayer predictions with respect to a distance threshold. As shown in this figure, our method significantly surpasses other methods at most thresholds. Next, we report the ablation studies into this table. Our method achieves the best results with the power of the Coplanarity-Aware GAN, and the implicit mask generation has a limited enhancement for homography estimation. We show the visualization of plane masks to demonstrate that our masks are able to focus on the dominant plane. These images cover various challenging scenes such as moving objects, large foregrounds, low light, etc. We can see that the masks guided by our Coplanarity-Aware GAN locate the dominant plane well. Furthermore, we also show how our model handles multiple candidate planes with some examples. When the mountain occupies larger areas, our method treats the mountain as the dominant plane and highlights it, and vice versa. Once the mountain and the forest areas are similar, our method will compromise to highlight both planes. Now, we show some image alignment results. These examples are more challenging due to the significant depth disparity in illumination. We can see that the other method's results compromise on multiple planes, while our method does not, thanks to the Coplanarity-Aware GAN. Next, we further show more examples in comparison with feature-based methods. In this scene, the mountains behind the island are almost stationary, and most feature-based methods are joined with the outlier rejection algorithms, which still fail to align this image as well as ours. This scene is a challenging low-texture case, and most feature-based methods cannot estimate accurate homography due to the insufficient number of matched points in such a scenario. On the contrary, without relying on key points, our method remains robust in these scenes. Our contribution can be summarized as follows. Firstly, we propose the Coplanarity-Aware GAN to address plane-induced parallax. Secondly, we propose a multi-scale homography transformer. Finally, our method achieves state-of-the-art performance. Thank you very much.